Welcome to Repelling the Earth, Low Altitude Flight. Topic 5, an Introduction to Aerospace Engineering. Over the next 4 videos, we will be talking about definitions and units. Then we'll talk about reference frames. Then we'll talk about the equations of motion for flight in the atmosphere, i.e. low altitude flight. And then we're going to talk about the concepts of trim and stability, specifically longitudinal trim and stability. In the next topic, we will deal with the same area for high altitude or space flight, so stay tuned for that. As with all of our sessions, we will begin with a couple of cartoons. Sorry to interrupt you, folks, but we've just had a report of some turbulence ahead. Please stay in your seats for a little while. And then you see, obviously this isn't how turbulence really works, but it's a nice thought. Or how about this? Yes, what happens when you communicate wrong or don't realize what your flight's going to do? Later in the semester, we're going to move from the equations of flight with propulsion to performance and see how that works. Okay, so the questions over the next 4 videos, I want you to think about and come to the conclusion of how and why an aerospace vehicle flies. Specifically, in this case, a low altitude vehicle, an aircraft, fixed wing, rotary wing, the like. We need to think about what measurement conventions do we use. And the key thing here is convention, because there isn't a right way. And we'll talk more about that, especially with units and reference frames. What are the reference frames that we consider important? Specifically, the Earth, the wind, and the body, and we'll talk more about those. And then when we get to the flight, trim, and like, what is steady flight? What is level flight? And steady, level, steady flight. And then what are important non-dimensional numbers and coefficients that we use? And we'll talk about those and introduce those. And then in several weeks, we'll talk more about them, their derivation, and what they mean physically. So let's start with definitions. These are important for terms of reference, and I want you to peruse them at your leisure. But there are some key ones that we'll talk about as we go through. So let's talk about these definitions. They're in the notes. Please look at them in your free time. But some big ones that you're going to see a lot more in this unit are speed of sound, Mach number, up, and velocity. All these other ones, incompressible flow, subsonic flow, hypersonic flow, and the like, are useful and important for aerospace engineering. And I want you to start to remember them. You'll probably be talking about incompressible and compressible flow in fluids. Next year in fluids, you'll definitely talk about supersonic flow and supersonic flight. And just remember, the difference between flow and flight is basically, is the fluid moving or is the vehicle moving? Okay, so speed of sound. This is the speed at which pressure disturbances travel isentropically without generating entropy, i.e. losses, through a medium, be that air or water or solid like steel. And it is basically the relationship between a change in pressure and a change in density. So if we get a d rho, a change in density, how much does pressure have to change or vice versa? A squared is equal to dp d rho. And for a perfect gas, an homogeneous gas like the atmosphere, A squared, that's the speed of sound squared, is equal to the quantity gamma, which is the ratio of specific heats, which you'll learn more about in thermodynamics, R, the specific gas constant for air. And remember, in the homosphere, it's a mix of 79% nitrogen and 21% oxygen that we use, and the local temperature in absolute sense, so Kelvin or degrees Rankine. As A goes to infinity, we say that the medium, the air, the water, the fluid, becomes incompressible. That means that information, pressure information, basically travels instantly from one side to the other. If A goes to 0, it becomes infinitely compressible, and that's what we represent as effectively hypersonic flow. So incompressible could also be called hyposonic flow, as in so much slower than the speed of sound, we don't really care about it. Mach number is relatively easy. It's named after Ernst Mach, a Swiss mathematician, and it is basically the ratio of the velocity of the body or the flow to the pressure disturbances that travel through that, V over A. So the velocity over the speed of sound. As you get closer to the speed of sound, your Mach number gets closer to 1. If your Mach number is above 1, it's supersonic. Okay. The next two at the bottom that I want to bring your attention to are up and velocity vector. Up is a really interesting one. How do we define up? For the purposes of this unit, we're going to say up is direction directly opposite to the local gravity vector. So obviously, if you're in a strange place and gravity is at a strange angle relative to the surface, up may be different. But generally in Earth, the gravity vector is down through the surface of the Earth. The velocity vector is just that. It's the direction of movement of the aircraft or the local wind. So if I'm standing still and there's a breeze blowing in my face, there is a velocity, a wind velocity vector. If I'm running through still air, there's a velocity vector. If there's both wind and I'm moving, it is the combination of those two vectors, the resultant vector that we care about. Okay, some additional definitions. And these are really important ones here at the top. The first one is lift force, and its forces resolve perpendicular to the velocity vector. So we tend to think of that as up, but keep in mind that could be any direction. And it's not relative to the body of the aircraft, it's the velocity vector. So when we get to the equations of motion, we'll talk more about that. And we'll have some asides where we look at the aircraft of the glider and how that works. Drag force is just forces resolved parallel to and opposite the velocity vector. So there's your lift and drag. We have thrust force, which comes from a propulsion system, and it does not have to be aligned with the velocity vector or even the body axis of the aircraft. And we'll show you more of that in those things. Normal and tangential forces are those lift and drag forces, except for instead of being resolved to the velocity vector, they're to the body axis of the aircraft. The next three are our pressures: static, dynamic, and total. We're all very familiar with static pressure. It's the air pressure you feel around you at any given time. Dynamic pressure is that pressure which you feel and is induced by motion. And we use the equation and representation of Q for dynamic pressure right here. And Q is defined as 1/2 rho times the velocity squared. And that means you can have a local dynamic pressure around a given point on an aircraft, or what we call the free stream dynamic pressure. That's the dynamic pressure and properties far away and not affected by the aircraft. In aerospace engineering, especially in aeronautics, we tend to quote everything in terms of free stream dynamic pressure, what's called Q infinity. Then, because we have static and dynamic, if we add those together, we get the total pressure. And that is effectively the pressure you would feel if you brought a moving air mass to a stop. So it's the static pressure we feel, and then the dynamic pressure. It's P naught, which is different from P naught, meaning sea level pressure. So same note of terms, same notation, different meaning, something to worry about. And that is just P static pressure plus Q. What that means is if I'm standing still and I start moving air around me, the pressure at those places with velocity has to drop. Something you'll be familiar with from fluids, Bernoulli's equation, whether you've gotten to it yet or in the future, that's that relationship. Free stream, as I said, which we represent with the subscript infinity, is just the properties far away from and not affected by the aircraft. Then we have things called chord and reference area, and these are some non-dimensional or non-dimensionalized things. They are relative to the aircraft. It is up to you to choose them, but in general, for fixed wing aircraft, the chord is the length of the mean aerodynamic chord of the wing. So it's from the leading edge to the trailing edge. For your glider, our wings are relatively constant chord, so it is just that geometric. Reference area, again, you get to choose it, but for fixed wing aircraft, we tend to use the planform projected area of the wing. We can add on to that other types of vehicles. For cars, our reference area is usually the cross-sectional reference area. That's the same for rockets and missiles. But what that means when we talk about coefficients in the future is that you cannot compare the drag coefficient of a car to that of an aircraft until you compare the reference areas. Okay. Next, we're going to talk about units. And units are very important to what we do because we work in units all the time. And your understanding of units is really going to help you with the stuff that comes next. First of all, the most important thing you can remember about units is they are inherently arbitrary. While they may be based on some reference, such as the circumference of the Earth at the Greenwich meridian or the circumference of the Earth at the Paris meridian, they are inherently arbitrary. I can choose anything as my reference point for unit of length. In fact, if we look at our physical constants, Avogadro's number, Planck's constant, Boltzmann's constant, they don't work evenly with any of our conventional unit systems. So whether you're using SI or customary or metric or goofy American, you can define any set you like. However, within that, there are two basic types of unit systems. They're what we call consistent and inconsistent units. And the beauty is consistent units are the easiest ones to work with. They are absolute and they are related to each other through proper constants. So think of the most common consistent unit set that you'll be familiar with, SI. We have meters and kilograms and seconds and candela and things like that. And we can relate length and mass and time to things like force through the local acceleration due to gravity. So 1 Newton is 9.81 meters per second squared times a kilogram. So it's kilograms meters per second squared. An inconsistent unit, such as the metric system, would then use a different thing. So there you might have kilograms of force, where the G is effectively 1 meter per second squared. If you have a choice, I always recommend you use consistent units. However, there's some nice places that you'll see, especially in aircraft performance design, where using inconsistent units is very handy. It doesn't matter if you use SI or US customary. There is nothing about it that is preferential. There's nothing about it that's inherently better. Yes, we tend to think better with multiples of 10, maybe because we typically have 10 fingers and 10 toes, but that doesn't mean it's inherently better. In fact, base 10 is an inherently inferior mathematical base to base 12. Not that US customary really uses base 12 or base 60, which we use for degrees, minutes, seconds, arc lengths, and the like. However, my one recommendation is always to stick to one unit set. We have inconsistent units that we're familiar with: hours, kilograms force, the calorie, degrees Celsius or degrees Fahrenheit. And then we have what we call our joke units, but they're just as valid as any other unit. The smoot, for instance. But we also have things like BTU and horsepower, which you hear all the time. So now we're going to do a little aside on the history of the smoot, and then we'll come back to this discussion. And now for a quick aside on the unit of the smoot. This begins in 1958 on the Harvard Bridge, which goes between Boston and Cambridge, Massachusetts. I'll give you a second to think about what university the Cambridge end of the bridge is at. No, it isn't Harvard. The Harvard Bridge is named after John Harvard, the person who gave his name to Harvard University, but it doesn't go to Harvard itself. On the Cambridge end of the Harvard Bridge is the Massachusetts Institute of Technology. In 1958, Oliver Smoot was an undergraduate at MIT. One night after a fraternity party that probably involved a lot of alcohol, Oliver and his fraternity brothers came up with the crazy idea of measuring the Harvard Bridge. And what they did is they took Oliver and laid him end on end along the Harvard Bridge to figure out how many Oliver Smoots it was in length. The Harvard Bridge turns out to be 364.4 smoots long, plus or minus roughly about 1 year for measurement error. Every year, his fraternity brothers mark the bridge as it stands. And the Harvard Bridge looks like this. We start in individual smoots, each one which is about 5 foot 7 inches long, or 1.7 meters, along the bridge from the Boston side to the Harvard side, or the Cambridge side. The Cambridge side is marked at the end of the bridge at 364.4 smoots, plus or minus 1 year. Now, Of course, you want to mark the halfway point in the bridge, but being MIT students, they didn't settle for just a simple number. They actually put halfway to hell. At another point, 355 smoots in, they mark it in binary. So that's the smoot. It's a perfectly reasonable, perfectly valid unit of length. However, by convention, it is typically only used in one place in the world. So we might ask you about smoots in the future, and you might be given something in smoots where you have the opportunity to look up the length. You're not going to typically work in smoots. And that's our aside on smoots. We'll get back to our units. On our unit conversion. Because we will be given units in different unit systems, different references, you need to be able to convert. Remember, in aviation, we talk about distances in nautical miles or meters. We talk about altitude in feet, and we talk about temperature and pressure in degrees Celsius and bar very often. So how do we convert between all of those? Here are some units conversions of the like. Again, we have the ones in red, and these are the ones that are the most important unit conversions that you will have to do. These are the ones I expect you to be able to remember over time. Obviously, you can have them on a cheat sheet, but the sooner you become familiar with them, the better. Our nautical mile. That is defined strictly as 1,852 meters. Now, the meter and the nautical mile arose from the same basic principle. How do you divide the circumference of the Earth into even and distinct units, subunits? In the case of the nautical mile, we started with the Greenwich meridian and the circumference there, and we took 360 degrees, and then we took minutes and seconds. And it is 1/60th of 360 degrees around that circumference was the original source. The meter was similarly done for the Paris meridian. Now, those two meridians aren't exactly the same circumference. So in the late 19th century and early 20th century, they standardized and they chose this relationship as being the definitive. So the meter no longer matches the Paris meridian and the nautical mile no longer matches the Greenwich meridian, but they are now defined as 1,852 meters. A foot is roughly 3.28 feet per meter. And the rest of those are things that are useful. Fortnight, a day, an hour. Something to remember, a day is 86,400 seconds. Comes in really handy when you're doing certain aircraft environmental metrics. And then, of course, we have our conversions between our temperatures, between our relative and our absolute temperatures. And the big one to remember is the difference between Kelvin and degrees Celsius at 273.15 Kelvin to get to 0 degrees Celsius. Okay? And that brings us to the end of units. In the next video, we're going to talk about reference frames and forces. And in the following videos, we'll talk about the equations of motion and the concepts of trim and stability. So stay tuned for that. Thank you again.